2.6, and I have posted the solution for that, but I'm going to also explain it here. First part of this question is that ddz of g of z versus, it's an analytic function, g is an analytic function, and ddt of g of z. So I ask you to explain the difference between these two things. This is a derivative of complex numbers, and this was explained with, here if you look at this point, and this velocity vector and that velocity vector is mapped under this function to that velocity vector that, if you move it here 1 unit, and it's actually, the image is moving toward a different direction with a lot potentially faster or slower, right? What about this one? If I go up, what is the direction under this function? It's reviewed as an xy variable, UV images, right? Remember that part? And remember what happened to that guy? Exactly the same length, remember? And relationship between this one here is 90 degree. Okay, it's a 90 degree. Exactly 90 degree in there. So that was the dt level. If you do it up to here, that becomes dt level. But what is the final bit in the calculation? The complex number in the denominator, right? The ddz, right? The complex in the denominator also involves rotating backwards. So if you go in here, divide by that complex number, and then it's coming back in here. So always pointing this direction. So the answer here, g prime of z, is, which one is that? Is it this one or that one? Number 1 or number 2? Which one is this g prime of z? This one, the other one, is putting it back to its place. Wherever the other direction is, you have to rotate it back to this position in there. So this one is the answer. This one is obtained by moving to that direction, right? As this point moving to that direction, is x varies or y varies? Is this point moving to that direction? X point varies in the domain, right? Y is fixed. So what would that be here? Which derivative is that? X derivative and x derivative in here. This is kind of odd formula. You've looked at it before. Now you look at it again. What happened to y's? Where is y's, right? What's the explanation? If somebody asks. What happened to the uy vy? Where did they go? Yeah, it rotates backward. It doesn't give you uy vy, right? But you can rewrite it as in terms of uy vy. How do you do that? What equation do you use? Say that again? Right. What equation is this called? Cauchy-Riemann equation. You can write it like this, right? Okay. So that's a g prime of z. Usually people prefer this version. Ux plus ivx. That's the meaning of g of z. This one is really separating like this u plus iv. And no more complex algebra. This derivative of u is done with respect to t, and derivative of v with respect to t done separately and written separately. So this is exactly d dt u plus I d dt v. That's just the meaning of this one definition. Okay? Just like vectors. U is x component of a vector, v is y component of the same vector. Okay? And u is originally a function of two variables, x and y. Correct? So what is this? How do you... I'm differentiating with respect to the additional parameter t, right? And u is a two-variable function. So only thing that makes sense is that x and y is parameterized in terms of t, one variable, right? How do you differentiate this thing? What rule is that? It's two variable. Chain rule. How does the chain rule work? You do the partial first, right? And then multiply by dx dt, right? Dx dt. uy and dy dt. That's the real part with respect to t. And the same goes for the other two variable function, like that. All right? That's the meaning of ddt and zt. I didn't expect this much of detail. Just one way or another, you describe the difference between the two. And part B is asking you to prove that fundamental theorem of complex integration, part 2. What was that? Let me emphasize the context here again. Here's a proof. We're given that antiderivative fz exists such that f prime of z is fz. That's an meaning of f antiderivative, right? And exists. Do you know what the fundamental theorem of calculus part 1 is? This is a part 2. If you were lucky enough and found an antiderivative, and this is how you calculate integral, that's the fundamental theorem of calculus part 2. Does anybody know what the part 1 says? It gives you an integration formula, definite integral formula of this f of z. Therefore, it implies it exists. And here in part 2, we start with we found it. The existence is given, and part 1 is showing that it always exists if it is a continuous function. Okay, that's a part 1 and part 2. Mostly we use part 2 and never think about part 1. Right? But if you're math major, you have to think about part 1. Why is there antiderivative all the time? That doesn't mean we can write down a formula, right? It only, in one form or another, it just exists. Okay, but right now we are given this existence is given, and we want to prove. What is that we want to prove? For simplicity, if you put simple closed curve or path, is that the path? Is that how I formulate it? So it should be a path beginning and end z1 to z2. fz dz is fz2 minus fz1. Is that right? That's how we do it. So we're going to prove this one. So first thing we're going to do is that we're going to go through the actual definition of this line integral, or this complex integral, and switching to the dt. So that's why I brought this up. So here, proof goes like this: lambda fz dz. So what was the very definition? No antiderivative, no nothing. It's just what was the very definition that I was introducing here? We passed to a to b, right? Plugging in actual parameterization, no Cauchy's theorem or anything. Then fc is going to be there, and what do you multiply when you switch to dt? This is a complex multiplication. Think about e to the it. When you plug in this e to the it in the complex integration, what do you multiply at the end? Derivative of e to the it, right? So you have to multiply dz dt. Okay? And we use now this little fz is derivative of something. So here's f prime of z is dz dt in there. Okay? Now this one has, real part written in terms of t and imaginary part written in terms of t, right? And you separate it and integrate both parts, and that's how you actually calculate this one in terms of. But what triggers you thinking about is f prime of z and dz dt. What rule, if there's some differentiation rule, derivative rule, if you apply it, it looks just like it. What rule is that? It looks just like the chain rule. But it is done through dz dt with the real variable. But it just looks like a chain rule, and we used it many, many times throughout the courses, but actually we never calculated. And that's why I have written down in here. If you switch from this little g is a capital G, and you have to argue that this one here is that f prime of z times dz dt is actually ddt of something, right? What do you think? We're discussing two things. Differentiating complex variable with respect to z is just simply called, g prime z. But if you differentiate a complex function with parameterization, then that's the a different meaning. So this one is actually that f of z. Okay. So the proving these two things are equal, it seems like a chain rule, but this type of chain rule is actually never thoroughly proved. If it is a dz, so let me compare these two things, f prime of z and dz ds, let's say dz dw, where w is another complex variable, then this one is easy. That's the usual chain rule. Okay? But t here is not complex variable, it's a parameter. You have to establish this one through this mechanism and through separate calculation of these two things and show they're equal to each other. And in that, it actually uses CRE. It's absolutely non-trivial calculation. And I did that, and if you wanted to see that, and you can verify yourself. So in that solution in here, I actually proved this one in that. So I want you to take a look at it. So here I'm going to skip that. So here's this one is a to b, and you can replace this one. Let me write it like this: ddt. It's more vivid of what's going on in here, like that. Before, some derivatives multiplied that by chain rule, inside the integrand is actually a derivative of one function, right? Again, this one looks like ddt of u plus I times ddt of v, not antiderivative of complex functions. This is how we're looking at it. F of z has a u part in that, right? A real part, and v has imaginary part, all in terms of t. So this is what we're looking at. So here is the ab d dt. There's a u in terms of t value dt, and I ab d dt v in terms of t dt, like that. By definition, the meaning of this one is this, if you separate a real part and imaginary part of capital F. But there's no complex number at all, and if you just look at part, there's no complex number at all, right? So what happened to that part? There's a real valued function only in terms of t after you compose it. So operation goes like this: differentiate and integral, right? This is the entire operation done. Differentiate and integral. Or integrate and differentiate later. How does these two operations work together? They cancel each other, right? Yeah. So it really be u and evaluated a and b plus I. V evaluated a and b, but that's exactly, if you put them together back into F form, then it's F2 minus F1. So that's that. Okay? So what happened here is I was just being careful with these two things. Not things as just looking at the same, so not being confused about this situation and that situation. Why does it get so lengthy and complicated like this? I try to distinguish these two things clearly, and that's why it happened like this. And in that, we use a CRE, and it's an important part. Okay. Next theorem is more